construction platform is very important, which can save or cost contractors a lot of money. And I started really get involved in bridge rehabilitation after like 9/11. When 9/11 happened, and the whole New York was in recession, so that the U.S. government and especially the Port Authority is the owner of these twin bridges. Once they collapsed, they got like billions of dollars of insurance money. So the government asked them to spend as much money as they can to stimulate the economy in New York area. At that time, because Port Authority not only own these buildings, they own many of the bridges in that New York area. So they did a lot of bridge rehabilitations. So at that time, I was involved in many of these projects. So at that time, the real challenge is like to stimulate economy, you need to bring a lot of people to work. And traditionally, you have platform, typically platform made of like aluminum panel, that kind of thing. It's very expensive. You cannot build a platform for a whole bridge. So a friend, actually my classmate, who had a small engineering company in New York, he developed a very, very good idea of having platforms. So what he did was he using cables to support platforms. Of course, if you design a cable from one end of bridge to another end of bridge, the force will be so large that you effectively have to build a suspension bridge. But for bridge rehab project, the good thing is that you already have a bridge there, so you can hand cables to the existing bridge so that the force in the cable will be manageable. So that's how this platform was introduced. So these are these cables. You can have different layers. So the platform, all the force in the cable actually is not very clear. It's almost like an equation of a bending moment, 1/8, which is also proportional to square of the span length and the uniform distributed load. So, and reverse to the diffraction, the delta. So, like it's very easy to manage the force. So you can have the hangers to hang into the existing member so these are the load tests 2 years. But to have these cables, of course, alone does not work very well. So originally, he was thinking about put some like a timber, like a plywood or aluminum panel, but that's not very efficient. So finally, he had a very good idea. He just introduced like a chain link fence type of like materials put into on top of these cables, and that's why they had a name called total containment system. Basically, just like that, and it can have multiple layers, and that also can use for like a paint remover, so like produce a containment for lead paint remover as well. So, and of course, like if you have simply just this chain link fence, it will be relatively soft. So that's the only thing. So usually they will produce a localized like either aluminum panels or just timber panels for the working area. And by doing that, they can have like hundreds of people work on the bridge simultaneously. And like these are typical installations of cables, and then they have chain link fence. And so that can be used as a platform And also use as shield, like if you want to remove a deck, sometimes the debris may fall off. So that will give you a protection of like a debris. And these are like transverse intermediate. Like sometimes you don't have place to hang to support these cables. So you can have like a steel tube. This steel tube will be hung into these main girders, and these cables will be supported by individual tubes. Yeah, these are the installations. So only during installation, it's like workers need like safety protections. After the installation, it's very good, and so that there's no like support from underneath, so there's no traffic interference. And also, you can specify what the size of these grid, so that you can basically just collect most of these debris. So basically, when you consider bridge rehabilitation, it mainly most of the information will come from bridge inspections, and also the bridge inspection will also feedback to see what the original proposed rehab makes sense. So sometimes, initially you think you want to do this. After inspection and study, you may alter your course. So that's why inspection is always very essential element for any rehab project. And also like sometimes survey data is also very essential to get accurate information, especially if you may have like a vertical clearance issues and other like maintenance of traffic issues. So these are basically the elements you may want to consider during the rehab. The big consideration you may have to deal with is a detour and the staged construction, where we actually have a separate discussion on that issue. That really affect the cost and affect how the bridge is built. Like if you can detour, in other words, if you can shut down the bridge and let people using another alternative bridge, that can speed up the construction quite a lot and reduce the cost. But if you cannot do that, you may have to do staged construction. That is very time consuming and also affect quality and of course affect cost. These are basically all these considerations. As I said, the staged construction and detour is very much essential elements of these considerations. And another thing we need to emphasize that whenever we have a steel girder, try to make them composites. That is not something costs much money, but it really enhances the bridge performance quite a lot, and also make a simple span continuous. It can be like a steel girders. It can also be concrete girders as well. Like I'll have a sample in like this afternoon, show you how to make that. And also when you do the inspection, usually you predefine what kind of item you need to report immediately, so that you don't want just give them only an inspection report. So if you see something really essential, really urgent, you need to report immediately. Of course, once you do that, in many cases, originally you have a inspection contract. And they say, oh, well, that's really something you need to do right away. And they may say, okay, can you do that design for us so that you actually expand your scope of work and get extra work. And that's why it's always essential to predefine what kind of item you need to report back to owner immediately. Another thing for government agency is that it's better for any agency to establish a on-call contractor. I don't know here, but in the United States, if you have a contract, you need to have a bid process. You can just simply call, like, Jose, can you come over and do the repair? You have to have open bid. But that's good for like a big project or a new project or large project which involving a lot of design. But if we see something like urgent needs repair, it does not work. So that's why you either, if your organization is big enough, probably you should have some kind of in-house repair capacity. This can also do like a routine maintenance. If not, probably it's a good idea to sign to have a bid process. Say, okay, and I have, for next 5 years, I have a lot of small emergency repairs. So I advertise, contractor can bid, so that I don't know what we'll be doing. So that what I can do is establish a profit margin. For example, I guarantee you 10% profit. Everybody can bid. And some people may bid, I only need like a 6% profit. Some people bid like 7%. They may just choose one or two. The contractors say, okay, sign contract so that I don't know what the scope will be in the future, but when I need, I just call you and give you a percentage of profit, so that in the future, whenever you have emergency, you don't need to go through the procurement process again. So that you already signed the contract. We call it on-call contractors. So this will be the rehabilitation section. And so we'll continue to next one. Yeah, last section is the largest. Basically, that section deals with most of the bridge repair work, which is probably like 80% to 90%. The rest will be, we already mentioned that. The rest will be more like a specialized repair, which include like scar damages, include like earthquake damages, and include like fatigue damages. So structural fatigue is a phenomenon for steel members, although to a certain extent, like a concrete or post-tension, especially pre-stressing steel, may also experience that. But to most people's knowledge, we haven't had such issues in practice. That's why when we talk about fatigue, we typically deal with steel structures. Basically, fatigue was not a phenomenon known to engineers until 1950s. Although in the early stages, like in the 1920s, 1930s, there's a university called Lehigh University, professors already noticed that phenomenon. But at that time, they only noticed something in brittle materials, like cast iron, or ceramic, that kind of material. Because at that time, like a ductile material, like steel, was considered very ductile, did not have such issues. And they did the research, and that research continued until even now. That's why Lehigh University is still the pioneer for fatigue research. And almost most of the research comes from that university. Actually, there's Dr. Fisher, who just retired. is considered the expert. In other words, most people will refer to him for the previous research. So basically from what we understand now is that fatigue is something like no matter what, in the fabrication process, there's always an initial defect in the material. We consider steel as homogeneous, but it always has defect no matter what. So when you apply repeated load, not sustainable load, like if we have a load static, usually we don't have any fatigue issues. When you have repeated loading, and that repeated loading has to be intentional. If you have like repeated compression, we don't see any problem. And then the initial defect will progress gradually, and it will reach to the point that it causes like a visible crack, and then cause like a structural problem, or even further to the failure. So most people now think that the fatigue is a phenomenon of actually accumulation of energy. In other words, like if you apply a load to it and release, and apply load to release, although we consider steel as like an elastic material, but every time you have such a process, you have very tiny fraction of energy lost for that whole process. That loss of energy is absorbed by that defect zone. So in other words, it is a total accumulation of energy that is cause the problem. That's why fatigue is a very slow growing process. And we know that since that's the nature process and you cannot avoid, especially for bridges designed for truck traffic, and truck comes and go, not like building like when people like if you have designed for library, you put box there, that box will be sit there for 20 years, so that you don't have like cycles. So that's why that's typically is for the problem of bridges, and especially for highway bridges. For railway bridge, like we have trains, but we don't have like thousands of trains per day. So the bridge life is very much similar. It's about like 75 years or 8 to 100 years. But in the railway bridges, they don't have that many trains per life, so they cannot accumulate that many energy to cause fatigue crack. That's why we typically don't see any fatigue problem for railway bridges. So that's why, but on the other hand, research also found that if your stress level is very low, your fatigue life is so long, you can almost consider it has an infinite life. How low is that? Is typically it's about about 50% of a year stress. So like for example, if you have a year stress of that, and if you keep the maximum stress of that, that would be in other words, that will give you infinite fatigue life. And people say, well, that's good news because we're not design bridge. I have like load factors, resistance factors, and also if we take all these factors away, my design stress is less than half. That is the reason why fatigue will not occur at regular locations. In other words, if we have a simple beam for their design, you don't need to worry about any fatigue because anywhere the stress will not exceeding the fatigue threshold that is half of its capacity. And research found that you don't have to worry about fatigue if you don't have a special design. And not special, just a strange details. And that's why in the ASHTO they found that They have different details. So really why we have fatigue that because the designer designed something which causes stress concentration. In other words, like if you have all of a sudden section changes, like if you have a regular beam and I put a cover plate, a weld a plate there, and at the end of the plate you have all of a sudden a section changes. That causes stress concentration, so that because stress concentration at that point, the stress typically exceeds that the half of the yield capacity quite a lot. So that's why it's, that may cause a fatigue problem. So in other words, to look at fatigue, you don't have to look at bridge anywhere. You only look at where you have a stress concentration. And that's why when you do the design, try to avoid. So we'll continue that. Basic illustration, especially welding. Welding is even worse than the fabrication of steel. When you manufacture steel, usually it's really good. So you may have isolated defects, but that's not significant enough. But welding, usually it's much less quality than the steel. So most of welding may have an initial defect. Like for example, you have fillet weld, you have an initial defect, and you do the test. That defect will actually, every time you do a load test, you have tension there, so it may accumulate energy there, and until it's reached, actually every time accumulate, and because you have discontinuity here, normally what happens is that once you have a discontinuity, it has a very, very high stress concentration at at the tip of these defects. So in reality, that the stress there is very, very high, but it cannot be too high. Once it gets very, very high, it will become a yield. So at each of these defects, when you have a load, it actually has two plastic zone. In other words, this will be plastic. That's why whenever you have plastic, when you apply load, it will absorb energy. In other words, it won't, if you apply 1 joule energy, and when you release, actually you don't get 1 joule energy bounce back. You keep maybe 0.001 joule energy, so that every time you accumulate. So that means that plastic hinge may grow a little bit, and the crack may become bigger and bigger. So once you have thousands of cycles, so it will become bigger and bigger, and so that become bigger, and that's plastic zone. And once the crack is so large, your section becomes smaller. So all of a sudden, because section is too small, so it just break. And once that break, this breakage is not plastic. In other words, it's not caused by plastic zone. So it's usually will give you a very, very brittle, very shiny surface. And that's why if somebody asks you to do an inspection, see what happened, that bridge collapsed. And if you see this, a section like this, with very, very crystal, these kind of crystals, and so it's typically caused by sudden fracture, which is typically fatigue, because steel should not happen like that if it were not a fatigue. So typically we know the fatigue phenomena is you cannot avoid. So what you can do is that you can do two things. You can monitor it, inspect it, but you don't really need to inspect it and that much. You can calculate the fatigue life. It's relatively straightforward. So you can predict fatigue life because you know how many trucks will be passing on the bridge. So and you will know, you'll be able to calculate how much actually the cycle will be. So, but how you how you get the equation? Right now, there are two ways. And there's a mathematical equations, which is based on the theory I mentioned. They use accumulation of energy. They calculate accumulation of energy to calculate how much energy is required to cause that crack to grow. Actually, they can calculate how much grow, and once it grows to how big you assume structures failed. So they use that accumulation theory. That's typically done by mechanical engineers. But for structural engineers, like building or bridge structural engineers, we don't use that because that's too complex. So what we did was we did a lot of research, basically just testing. I just do testing to see if we apply a tension release, and see if we apply that big force stress, and see how many cycles I can have, and I increase and to see. So you can have a lot of these dots, and once you have these dots, you can develop a SN curve. S means what stress level is. What stress level and what N means how many cycles you can have. So they have a lot of dots, and they found the relationship between the S and the N curve. So that's how ASHTO is used. In other words, ASHTO does not give you a mathematical equations, but it tells you what kind of S will produce what kind of N. So it will be discussed later. Basically, from our structure point of view, but from mechanical engineer's point of view, I just mentioned, they think it's just continuous accumulation. It's just it's always growing, the defect or crack. It was originally grown very, very small and become quite quicker and quicker. But from our, I guess, structural engineer's point of view, we assume there are different stages. At first stage, it's just barely visible crack. In other words, the crack is almost like a dormant. It never changes. Like if you go there, take a look, and later take a look, it doesn't change much. And at second stage, it's starting developing. And the third stage is just at failure. It's once it starts developing to become so big, it reduces section properties. Once it reduces section properties, that increase your stress, so that become like a spiral, so it will be failed very quickly. So that's why we typically say there are 3 stages. So the key is detect the stage in that stage, detect fatigue in that stage. Once you get into this stage, you're in a very dangerous situation. Like if you see crack like that, probably you say, okay, I'm really, really lucky to detect that. Otherwise, the bridge will be collapsed very quickly. So when to find crack, as I said, without stress concentration, the bridge element should have infinite fatigue life, because once you take in consideration of all these factors, it should not reach that half of a year stress anywhere. And but once you have concentration, so that's one thing. But after that, the recent research found that it is not only stress which causes the fatigue. The bigger phenomenon on the bridge is that a lot of fatigue crack is caused by deformation. In other words, if you have a lot of deformation in that area, it causes fatigue. Like for example, if I have transverse members, and if you attach to, for example, if you attach something like that, that has a force, and that keep on moving, so that causes crack a lot. But for deformation induced, still we don't have a theory to quantify it. So if we don't have theory to quantify it, what we do is, the ASHTO says that you should not use this detail. You should not use that details. In other words, to avoid such detail. And the typical fatigue crack is is caused by like stress. Like for example, and this is like a stringers, this is like floor beam. A lot of old bridge has like old bridges, we try to use at early stage, like in the 50s, even to the 60s. At that time, labor is relatively cheap, material is expensive. So when people talking about optimization of design, typically they say, okay, if I design a structure with less steel, it's my optimization. Now we change the concept. For design optimization or value engineering, we were talking about the construction cost as a minimum. But actually, now we expand that. We were talking about life cycle cost. In other words, not only construction cost, you have to consider how much maintenance for that type of thing will cost. So that you talk about the whole life, like 75 years, what will be the cost. That's how we optimize. So once you have that kind of optimization, you try to avoid the complex details. You try to avoid difficulties during construction or fabrications. But anyway, if you only consider the tonnage of steel as optimization, which was the case in the early stage, like in the 50s, the designer tend to design with very, very few girders. Like sometimes there are only 2 girders, sometimes only 3 girders. The girder has a space so large that you cannot have a deck to span that long. Like for example, if you have like 5 meters spacing of girders, the deck won't be able to span that. So what you do is you provide floor beam, transverse beams to connect these girders. And you put the stringers on top of floor beams. Like these are the floor beams and these are stringers. And so that will give you the minimum quantity of steel. But people don't do that anymore. Most of like a bridge you design is they always have about same size of girders. Even if you don't need a same size of girders, like outside as like exterior girders, you still like I never designed an exterior girder which is smaller than the interior girder. I always have the same, even if you don't need. The reason that in the future you may want to widen the bridge so that it makes it a lot easier. And so actually that's a phenomenon we see a lot. And typically what people did was like, that's the size of stringers. So they see the size of stringer, they see how many bolts they can install, and they see if they can put six bolts, then they just calculate what the reaction is to see how many bolts are required, and if the requirement only 3, they say, okay, I provide 6, which is greater than 3. That's okay. But the problem is like when you design these, you assume it's simply supported. And if you have that many bolts, actually you have almost like semi-rigid connection. So you have a lot of bending moment in that area. That's why it causes cracks. When you do the repairs for fatigue issues, usually fatigue issue, if it can be easily replaced, you can just simply replace it. Sometimes, like if they're in major good members, if you cannot replace it, the best way is just to do some calculation to predict how long the fatigue will last, and then just decide based on that to see if you need to do anything at all. But if you need to do anything, we'll be discussing that in the coming slides. So first of all, the fatigue, for structural engineering design, the fatigue prediction theory is no theory. We're just using test data. Basically, just we test a lot of S as a stress level and N. The fatigue is not a stress; it's a stress range. Like for example, if you apply a load to just a simple tension. If we apply tension like 10 pounds and release to 5 pounds, 10 pounds, 5 pounds, 10 pounds, 5 pounds. So your stress level is only 5 pounds, not 10. It's a range. That's how, because this range will produce a energy which will be absorbed by the material. So if you keep on 10 pounds, never change, you never have fatigue because you don't actually release your energy. That will. So once you have SN curve, and they found like there's actually linear relationship of SN curves. Once you put, these are log scales. So if I have log scale and N and log scale S, it's almost like perfect linear relationship. That's how they produce and how the asters work. They will be talking about later. So once you have a lot of experiment, then you find like this is another question. Like I just mentioned the research found like if you have like about half of the capacity or the ultimate capacity of material, it can be steel, can be aluminum. Actually, most of metals they have similar characters, and you will not have fatigue problems. And also usually the fatigue capacity is also modified by just like a concrete. When you do the concrete test, if you have a very small cylinder, you get a little bit larger capacity than a bigger cylinder. The reason is that when you have a bigger cylinder, the probability of defect inside is much larger than a smaller cylinder. That's why you have a standard cylinder test. But sometimes, if you want to take samples from existing bridge, you don't want to have a bigger course. You have a smaller course, and your test is higher, so you have to apply a modification factor to lower that to a standard. It's the same, like if you have a different size, if you have larger size members, you have more likely to fail than smaller size. And also people find like a temperature also affect. If you have very, very low temperature, you have a much larger chance of fatigue failures. In other words, your N will be reduced. And there's others, a couple of other factors you may want to modify. So that endurance limit is, as I said, that half of the capacity. And also, some other factor you need to modify that. When we do experiment, we had especially before there was computer, you do the test. Typically you keep a constant S, like S. Like if you apply that S, you keep on having same S. Keep on doing until it fails. You count how many. And with computer, actually, we can do a random testing. In other words, I give them a range, like a S from a 15K set to 50K set. It's a random test. Random tests indicate that actually the failure, the N of failure is not the average of that. It's a little bit less than average. So that's a little bit important for us, is that because when the truck comes, the truck has different sizes, so different weights. So it's not really constant. Also, truck may drive a little bit here, a little bit there. So your stress is not really constant. So you may want to modify with how the stress is distributed. That's only for research. For design, you don't have to worry about that. So finally, from the graph with the SN curve, we can summarize like N is a function of S. S is basically just the stress range. And with these C and B factors, and C and B factors can be calculated based on your stress range and the capacity of that particular material, which is for steel we may use just yield stress. And once you have these, you have equations to calculate. So once you know S, you will be able to know the N. And so it will be relatively simple. So that for non-material, like if I know this, what kind of steel I have, I know these. So all I need to know is what our stress range is. So that's why if you know the stress range, you will be able to know calculate the AN. So the only thing you need to make sure that is these equations calculated based on stress concentration. In other words, when you calculate stress, you need to consider concentration. Like if I have a beam, like for example, if I have like that thick beam, that long, and I do a test, I test bending, and if load keep on bending at, then I found I got 100. Once the load reach 100, that member failed. And if I just cut a half and do a load test, like people may say, well, if you have half of then you will have, like because it's a square, I mean it's like a cubic of these. It will be like a cubic of the half of these. So you'll be able to calculate what load. But in reality, that when you apply the load, you get far less capacity. Because once you have cut, you have stress concentration. But on the other hand, if you just cut that beam into half and you do a load test, that will be the easy for you to predict. So the stress concentration is something normally people don't study in the mechanics of materials. It's usually in the fracture mechanics if you study that. And so that because of the stress concentration, and it's very, very difficult to calculate. Usually you need to use the finite element model to calculate that. And it's difficult for the ordinary designer to design. And usually when people develop ASTO code, they have assumption like people with bachelor degree should be able to design it. And also people with a hand calculator should be able to design it. So you don't need to use the finite element for every design of a bridge. So that because this you need to calculate the S. I mean that SE is after concentration of stress. So people say, well, how do we design a bridge? How do I predict a bridge for T life if every time I need to finite element analysis? Then people think, look at the bridge design. Actually, there's not too many different details. So what they did was, they said, let's put them into different group. Like for this type of detail, the stress concentration factor is that much. I put that into category. And for that, so once they have different categories, which already take into consideration of stress concentration, then they may just say, okay, let's have different SN curves for each category. So in that case, the stress concentration is reflected into the different lines of SN curve. So that the designer will not need to calculate stress concentration. You only need to look at what detail category is and just use corresponding stress. So that's what ASTO is used. So if you use finite element analysis, you can simply use this calculation directly, but make sure that stress concentration should be considered. If you use the ASTO SN curve, as long as you use the right curve, you don't have to consider stress concentration. Just treat that as a normal beam. And actually, that stress, as I just mentioned, like if you have a distribution of stress, in other words, not constant, you may need to have like a different ways to modify the global relation. And this is typically used by most people. Some people may use that. So this is stress, like we call the SN method, which is the stress life method. And like this is like a linear elastic fracture mechanism is typically used by mechanical engineers, as I said. This is a model which actually, I think it's more realistic and then more represent what actually happened. In other words, if you want to know the actual phenomena or actual behavior of the structure, these are the very good model and to do the calculation. Now, a real problem why people don't want to use that for structural design is that to do this, you have to assume original defect. Like if you assume original defect is 1 millimeter or half millimeter, that gives you a prediction of fatigue life totally different. And nobody knows how you define original defects. That's why it's difficult to use. And typically, when we develop a design code, there's another assumption is that when you have design code, different people should reach same conclusion. In other words, I want you to design, you should design the same thing as I did, unless we made a mistake. If we don't make mistake, we get same calculation. And if we use like this model, everybody gets different answers. So that's another reason it's not very useful for, or like a bridge design was not adopted. And like again, I just mentioned ASTO a little bit earlier. And so the ASTO is a SN method by eliminating the need for stress concentration calculation. But once you eliminate that, what you do is you develop different categories of details that were reflecting different stress concentrations. And of course, the shortcoming, there's a lot of, because it's simplified, so you cannot cover everything. So a lot of things were left without taking consideration. One is we don't really know the stress level, and we know how many trucks are there. But when we design, we assume the truck is 40 loaded, and actually even bigger than 40 loaded. But in reality, some trucks are empty, some trucks are not as heavy as we use in the design. So to reflect that, we use a load factor of 0.75. That is still higher than the average. But as I said, because we found when you have different load, the total effect is worse than average. So that's why maybe the average is only maybe 60% of design load, but we use 0.75 to reflect that distributions. Of course, sometimes there are multiple trucks, and that other many things it's left without considered. So again, we said, we have different categories to develop. This is called from ASTO. So we have different lines, SN curve, and these horizontal lines like that. If your stress level is not that high, if your stress level is lower than the endurance level, you have infinite life. So that's why for most people, when they design for fatigue life, they try to limit the stress level so that it will have, in theory, infinite life. Of course, if you look at mechanical engineering point of view, nothing is infinite because it just accumulates energy. But if it accumulates slow enough, and your bridge can last longer than fatigue life, then to us, in practice, it's infinite life. So only if your stress level is greater than half of the yield stress, that range, then you may need to using that SN curve to calculate the fatigue life. Actually, these are black very. Basically, then you can calculate how many years of remaining life of remaining life. Basically, how many years is like, first you calculate the how many, like n, how many cycles of the fatigue can be. Then you calculate how many trucks per year will be. Then you divide that, you will get a remaining life. Just like for like a fatigue value, just like when we do low rating evaluation, when you use a design approach, it's always very, very conservative. If you do an evaluation of old bridges, actually sometimes you may calculate, like the bridge is already 50 years old. You calculate the fatigue life is only 45. People say, well, the bridge should have collapsed like 5 years ago. So the reason that it's just too conservative, that's why we have different levels for fatigue prediction as well. So like, actually, it's reflected in these tables. So you don't see very well. So it has like three levels of one is a design level, another is a realistic, similar to operating levels. Another is a mean value. In other words, some research you want to predict actually really how many years of that life is. So that gives you like a most likely level, which is like on average. So, like a fatigue life prediction is actually relatively straightforward. As I said, all you need to know is to calculate what stress level is, and that's only for live load. Live load, and also with impact. Impact is considered part of live load, and then you just use what kind of detail just to get the right SN curve, and you will know, once you know S, you know the N. Once you know the N, you know how many years. And if your fatigue life is long enough, although you may have like a cracks, then you may not need to do anything. Or if you want to be safe enough, you just set up a like special inspection just to monitor to see if there's any progress. And so that's why not every fatigue crack needs to be repaired. But if you do need to repair, I think the typical measurement is like if you can replace the member, by all means, the easiest, just replace it. These are typically for like minor members, like connection members. Another is try to provide alternative load paths, like for example, if it were supported by these bolts, and you can provide a support so that for these stringers, so that it will not have further development. And sometimes you may just release some rigidities. Like if you have too many bolts, sometimes actually by releasing some of the bolts may also work. And which means the stress, another thing that if you have a relatively new bridge, and the designer forgot about fatigue check, and then later somebody say, well, the bridge should have like 75 years of fatigue life, and you didn't forgot to design that, and now you have only like 60 years of fatigue life. And what can you do? So research has found like because fatigue is the accumulation of energy, and actually if you have a little there's a kind of a small hammers, if you can almost like a massage. If you massage these crack areas, actually you can reset. And like if the bridge is already 5 years old, you do that once. Actually you can reset to the original stage so that you can prolong life for another 5 years. And another thing that if you have a fatigue crack, already had fatigue crack, typically what you can do is that because fatigue crack keep on growing because we know that stress concentration at tip. The stress concentration is almost like infinite stress. Of course, since they cannot be infinite, so it will be always yield. So what you can do is just drill a hole at the tip to release the stress concentration. Of course, like typically, that is in combination of other repair. People don't usually just drill a hole by itself. It's also part of other repairs. Yeah, another stress concentration is that, like when you design like steel structure, you cannot have a well over a well. Like if you have a longitudinal well and the transverse well together, if you cannot have the two wells two wells intersect with each other, and that usually causes a big problem. So what you can do is just drill a hole to separate these two wells, like that. And it's the same thing. Like you have two wells, you can just separate the stiffness. If the stiffness has that's longitudinal stiffness. I don't usually use longitudinal stiffness for bridges. I'd rather to have a little bit thicker web so to avoid, and I try to avoid transverse stiffness altogether, because the fabrication of adding this stiffness does not justify the saving of a little bit steel in the web. So like before you have a well in the longitudinal stiffness, and also you have wells over there, so they have intersection, you can just connect. Actually, you don't need to have continuous here at all, because the stiffener is just used to stiffen the web. So even if we cut off, that will be fine. Sometimes if you have too much bolt, you may release this, or sometimes you may even cut a U-shape to reduce the section properties so that you don't have a big bending moment here. Really a lot of stress, a lot of fatigue crack is not caused by stress. Of course, stress is something we discuss most because we know how to calculate. Actually, but more than 50% of fatigue crack is caused by uncontrolled deformation. So that, for example, if you have a member to connect to that, and that is a diaphragm member, so diaphragm has tension compression force, so that causes that member to deform. So that's why it causes crack there. So that is extremely difficult to quantify. So all can do is provide a member with sufficient thickness, or just avoid this kind of detail altogether. And one of the particular detail we have experienced problem is the concrete box connections. For typical piers, we have concrete, we will have column there. Sometimes there's a highway underneath, so you cannot put a column there. So what people typically do is they build a steel box, a pier, so that you have a girders connect to the box. And when they have load here, so that the diaphragm inside deform quite a lot, so that's caused crack, fatigue crack, because of this uncontrolled deformation. And that's actually the most critical detail we had is we call cover plate. Cover plate because as I said, when the bridge was designed in the 50s, at that time, people use allowable stress design. When you talk about using allowable stress design, typically you only need to have knowledge of like a second year student, which is calculate materials, mechanics of materials. So they will say, okay, I have basically my bending stress is proportional to my section properties, which is I, or you can calculate S. And if that's too big, my stress too big, I can increase my S. By increasing S, it's very easy. I can just wear another plate. But that's okay. But these cause stress concentration, as I said. Once the stress concentration is very large, so and that causes like a crack, fatigue crack. So that's why this kind of like cover plates is not allowed in most jurisdictions. So for this, like if you already cracked the problem, that bridge is already collapsed. So you don't have that scenario. But like you may have that concern that what happens if it develops into crack. So what you can do is that you can assume it's already cracked, although it's not cracked. So you can treat, like you can put like a splice plate, bolted, so we assume. So once you've done that, you effectively reduce the stress so much that it will not be able to develop crack. Or even if crack develops, you're not concerned because you assume it's cracked already. You treat that as a splice. Another thing is that just try to create an alternative load path. In other words, make original stress member redundant. Like for example, if I have this kind of corbel, and you have stress concentration there, and you don't know how they behave, and you say, okay, I don't care. I just bought a plates here, so that when I load here, these plates will take load, so there won't be any stress there. So then I provide alternate loads, and I don't care about that anymore. So that's the best approach. Whenever you have something you need to worry about, you just build something which can take over that load. And like that's also like for bearings, you assume it's a hinge, but in many cases the bearing is become frozen, and that you may develop cracks there. And in that case, you just bolt like two T sections to each side. And sometimes some people say, okay, before bolting these, I drill a hole at the end, then I bolt. That will be fine. And these are like bolting plates is the most popular ways to repair fatigue crack. But the problem is when you bolt these, it's visible to the public. So if it's very, very visible area and very sensitive area, people don't want to see that, then you cannot do that. In that case, you typically have to cut a V, like a V shape into these and provide a full penetration weld. We call it V and the weld. So first you just cut a V shape and just weld into that. And again, these are deformation based. Actually, a fatigue like that, and before, like in the 1940s, 50s, people don't know anything about fatigue. So when they design stiffeners, transverse stiffeners, they just weld the stiffeners to the web and to the top and bottom flanges. And later people found weld the stiffeners, transverse stiffeners to the tension flange. It caused fatigue problems and cracks. So later people say, well, you should not weld stiffeners to flanges. So they just weld to the basically just webs. And that's okay because stiffeners is to stiffen web. You don't need to connect to the flanges at all. But a lot of these stiffeners were also used for diaphragms. So once you connect diaphragms to that, the diaphragm has force, pushing. And like see that diaphragm. And the stiffness is not connected to that, so that these web become like out of plan, so that like in many cases they develop cracks, fatigue cracks there. So that's why now people later say, okay, now you cannot, you have to connect stiffness to the top and the bottom flange if you use that as diaphragm connections. And of course, if you do that it goes back to the original question. It may cause fatigue issues to the flanges. You also solve the problem for the web. Of course, that's one of the categories. And when you do the design, you should check. Normally, it is okay because these stiffness are not usually at the middle of the span. The stress level is very small. So what happens, like if you do have that situation, you can bolt like angles to the top flange and the stiffness, like for these kind of connections. Another thing, actually, it was not designed. We found a lot of problem of fatigue crack. It's caused by like we call tack wear. Tack wear is like when people do like erections, they want to temporarily stabilize it before they do the bolting. Bolting is actually relatively easy. Like before, there was no bolt, so people use rivets. They want to have these holes aligned because otherwise the holes will keep on moving around. So what contractor did was they just tack weld these connections so that the plates will not be able to slide, so stabilize. And these things actually, they never remove that, so that causes stress concentration. And so that's why now it's not allowed. And now actually you don't need it because we have both. Both relatively easy. You can put both in very quickly. But if you do have these, you should remove these. So actually, people did the finite element analysis, found the stress concentration for these is very, very large. That's why they have crack. These are typical repairs. As I said, for typical repair, usually you just drill holes at the tip and just bolt steel plates to replace these. And if you don't care about appearance, if it's look like very ugly, you do cut a V shape and weld them back. And these are the distribution of fatigue cracks. Actually, if you look at these, actually, most of these fatigue crack is caused by a deformation, not really caused by the stress. And these are the summaries. So again, you can predict fatigue crack, fatigue life based on calculations. And if you are not very certain about the fatigue detail, you can do like inspection. We call it special inspection to monitor it. And only when you feel really, really necessary, and only usually for newer bridges, you may have to develop a repair details. Because repair fatigue is very expensive. So, typical repair, as I said, is both plates and using like a V cut and weld back together. Okay, so any questions? Fatigue is the only issue for steel bridges. If you don't deal with steel bridges, probably it's not an issue. No problem? No question? Okay. Yeah.
I saw that you are in the slide that you are adding brace for the beams, but I would like to know if you check the structure of the superstructure of the bridge, when you already done the rehab, because if you are adding pieces, you change the period of the structures. So I would like to know if you check that, because some bridges could be getting to resonances. If you add another, I would like to know that. That's it.
And normally, it's really an engineering judgment. If you do very, very localized repairs, it may hardly affect the overall structure. Unless, as I said, if you make girder continuous, it was not continuous. Like if you simply add another plate to that, it should not be an issue. And
but you are adding dead load.
oh, that load is very, very, very small. Really don't need to consider that part.
And my second question is, have you ever checked bridge with isolated bearings?
Check what?
A bridge with isolated bearings? Isolations?
Oh, you mean for earthquake purposes? And actually, I never did that myself. There's a couple of large bridges in China. I was consultant to that. Yeah, they do use that a lot for, like for example, a Sutong bridge. They use basically just isolators to that to basically reduce the earthquake load. But that's typically it's not simple isolator. It is like a dynamic response instrument. In other words, the resistance is proportional to the elongation. When elongation is very small, like a normal vibration, normal condition, it does not have much resistance. And during earthquake, because the movement becomes very large, it will have big. And we also did that. Actually, when I was TYing, I was a peer reviewer for that Auckland Bay Bridge. That also has a big component for that. And I think most for two purposes. One is to control the movement for non-earthquake conditions. But for non-earthquake conditions, sometimes like for example, the Sutong Bridge was so long, as cable stay bridge, just the shake itself is almost like half meter. If you don't control that, it's just too much for the bearings and expansion joint. So that normal condition shaking should be eliminated by using some kind of dampers. And for isolators, typically used for buildings. In Japan, most buildings have isolators, so that it's almost like during earthquake, it breaks. It's like a light. If you have too much capacities, it just shut down by itself.